Okay, so let me start because we have less time before your first midsum exam, right? We need to cover a few things. So again, I'm using for the next 5-6 lectures slides of Professor Bush because these are very good slides. And if you want to make these slides, it takes a lot of effort. So I've taken his permission, thanks to him. So by the way, most of the stuff that we are going to cover is available in this book by Michael Sipser, Theory of Computation, or if you find this book difficult, there is another book by Motwani, Rajiv Motwani. Rajiv Motwani was you can call it supervisor of founders of Google, at Stanford. So he has also written a very nice book, which you can look at it. Okay, automata and languages and kind of. Okay, so what I'm going to cover, as I mentioned to you in the last class, so entire computer science can be summarized into 4 kind of machines: finite automata, push-down automata, linear bounded automata, and Turing machine. Okay, so we are going to study these 4 machines briefly. Essentially, if you look at any computer, there is a CPU and memory. This you might have seen this in your class 5th, maybe 6th, I don't know, right? At our time, it was not there, by the way. Now there are different components of memory: temporary memory, program memory, input and output in the CPU, right? So how does it functions? We have, suppose you want to compute, so function is f of x equal to x cube. So program memory has this program, compute x into x, then compute x square into x, right? Now if you take some input, say x equal to 2, it, temporary memory will do this computation based on program memory, and so the output is 8. Okay, this you are familiar with, right? Very basic computer science thing. Now, see, this whole process, CPU and program memory, is known as automation. Okay, so there is an input to it, output to it, and of course it can use occasionally temporary memory, right? So this whole thing is known as automation. So normally we describe it in terms of, so CPU plus program memory is nothing but described in terms of states and transitions. So states we describe in the form of a circle, and transitions, after receiving some input, you move from one state to another state. So there has to be a rule, okay, depending upon what input you are going to have it. So it is something like this: you are in a state this. After receiving some input, you go to via this transitions to another state, and so on and so forth, right? So bunch of these states with transitions, they are kind of abstract notion of your program memory and what? Huh? CPU, right? So now different kind of automata is possible. So normally people look at only these 3, because the 4th one, the linear bounded automata, is a special kind of Turing machine where the tape is limited. So the computation is allowed in a limited space. That's why it is known as linear bounded automata. Okay. So first is finite automata, where there is no temporary memory. Very simple form of machine. And well-known example, vending machine. You give a coin and maybe chips packet is out. Okay. Input, output. Very simple vending machine. Or elevator. You actually press, you want to go to room number, floor number 4. That is the input, and the output is that you can go there, right? So all those things are, so that brain of lift is based on finite automata. Okay. Push down automata. So we have finite automata plus one stacked memory. Stacked memory means there is, you can push something or pop something. Okay. So that is stacked memory. So push down automata, PDA. And then finally, the most powerful is Turing machine, which has random access memory. Okay. These are the three very, very basic classification of machines. And as I said, a special kind of Turing machines, when the tape is limited, you will see what does that mean in the next coming lectures. We call it as a linear bounded automata, which sits somewhere here. So there are four kind of machines. This is Mool Tattva of the entire computer science, right? The fundamental thing. If somebody asks you what is the summary of computer science? Summary of computer science is there are only four kind of machines possible. Finite automata, push down automata, linear bounded automata, and Turing machine. And there is a order. Push down automata is less powerful. Finite automata is having least capabilities. Push down automata is more powerful than finite automata. Linear bounded automata is more powerful than push down automata, and Turing machine is powerful among all. Okay, so this is a very, very basic summary. Now, memory affects computational power. More flexible memory results with the solution of more computational problems. So this is something you need to. So basically, what I am doing here, whatever computer you are familiar with, I am doing a mathematical abstraction of it. Okay, and to understand, so that we can understand the limitations, capabilities of the computer, what problems it can solve, what problems it cannot solve, and so on. So finite automata, as I mentioned, there is no temporary memory. There is only input and there is output. Examples of, as I mentioned, elevators, vending machines, lexical analyzers. They are having small computing powers. Okay, these are some well-known examples of finite automata. Okay, there are plenty of applications which are possible. So for you, as a tea time problem, just I will, by the way, I will show you towards the end how to construct finite automata. So can you construct a finite automata which can do, which has the smallest number of alphabets, I mean the alphabet size. Maybe I think, okay, I will first explain to you what it is so that you can actually really understand the question. Okay, maybe I'll come to that bit later on. So this is push down automata. Temporary memory is a stack memory. You can either push something or pop something. Parsers for programming languages are well-known examples of push down automata. Okay. So medium computing power. Turing machine. So the highest known computing power. Any algorithm is an example of Turing machine. Okay. And how it was discovered, as I mentioned to you, in 1900. Again, thanks to mathematics. Of course, everything is because of mathematics only, right? That the birth of computer science was there because David Hilbert in 1900 asked 23, he actually listed 23 problems. So maybe you can just go and read those problems. 23 problems, and he said that the whole mankind will remember him for these 23 problems. List of unsolved 23 problems. Some of them are solved now, and some of them are carrying $1 million prize if you can solve them. Still, there is a much more to do than this competitive programming, right? So basically, not only you will earn money, but also you will be famous worldwide immediately, right? So there are 7 problems which are Clay Mathematical Foundation. So Clay Mathematics Institute has listed 7 of them. By the way, there are mathematicians who has solved one of this problem, and he has denied $1 million. He said that this is small amount, right? I think I mentioned to you. So it's all game of brain, right? So finite automata less powerful, Turing machine more powerful. Hardest problem can be solved by Turing machine. By the way, Turing machine also cannot solve many problems. And this is a very remarkable thing. Because see, the summary of computer science is these 4 machines. Turing machine is the most powerful, but then there are problems which Turing machine cannot solve. And that is known as Turing barrier. So there are actually, it's very, very philosophically, it's a very, very important thing. That means if we think ourselves as one of the machines, our brain. Okay, it's a computational machine, right? In fact, there is a very nice, whatever I told you, all these four machines, I am talking about in the terms of classical physics. But when we look at quantum physics, so there is a quantum finite automata, quantum pushdown automata, quantum linear boundary automata, and quantum Turing machine. So that is a much more powerful machine. And Roger Penrose, who got recently Nobel Prize, you might see. So I met him something around 2003 or so. So I think quantum Turing machine, he gave that inside our brain, in the neurons, there is a protein called tubulin, which can act as a qubit, the smallest fundamental quantity to do quantum computation. Okay, so consciousness is there because of that quantum computation. That's what they have claimed. And of course, there are a lot of debates and so on and so forth. But so, but the philosophical answer to the to certain question is that if there is a Turing barrier and you are thinking that our brain is a Turing machine, and since Turing machine cannot solve many problems, that means we will never have answer to certain fundamental questions which you might be having from the birth, right? Who you are, what happens after death, all kind of fundamental questions you will not be able to understand. So it's a simple conclusion of Turing barrier, right? Beautiful thing, right? By the way, one of the mathematicians I met, Srivastava, Professor Srivastava, so once he realized these things, he used to carry a photograph of Lord Krishna all the time, whenever he go, whether in a conference or anytime, So he realized that all this science has a limitation. Your computers has a limitation, right? There should be something beyond science and technology, and that's how, so he realized interesting things anyway. So as I mentioned, there are unsolved problems of Turing machine. In fact, the discovery of Turing machine happened because of this decision problem of David Hilbert. David Hilbert said that because he was a mathematician, a very famous mathematician, I think. If you look at, I think you might, I don't know whether you heard about David Hilbert or not, but he used to solve, mathematicians try to prove certain things. And he asked this very basic question: is there any systematic procedure through which I can prove any theorem? Right, some result, some observation, can I prove it in a systematic procedure? And that's the question he asked. And Alan Turing thought, he's asking me to, basically he used the word mechanical. Is there any mechanical procedure? That's the question he asked David Hilbert. And Alan Turing misunderstood it. He thought mechanical means he's asking for a machine. And then that was the result of Turing machine, discovery of Turing machine in 1936. Okay, and then he showed that there are certain problems, for example, halting problem, which cannot be solved by Turing machine. Okay, so that means the answer was negative, that you cannot solve. So basically, there cannot be a systematic procedure which can solve everything. So there is a limitation. It's a very, very important fundamental result from a computer science perspective, right? Now, in terms of time complexity, so Turing machines normally, initial Turing machines, there are two kinds: deterministic Turing machine and non-deterministic Turing machine. What do you mean by deterministic Turing machine? When for every input, you have a deterministic choice to go, where to go, right? That is deterministic Turing machine. And there are non-deterministic Turing machine. For every input, you have non-deterministic choices, multiple options to go. Which option you should choose, okay? So both the machines have different, uh, constructions and so on. And in fact, in terms of problem solving capabilities, we say that a bunch of problems are known as class P problems if you can solve those problems in polynomial time. The complexity of the problem is actually you can solve it in polynomial time on a deterministic Turing machine. Then it is known as class P problems. Then there is a class NP problems. So basically, class NP problems, if you can solve a problem in polynomial time on a non-deterministic machine. So those kind of problems are known as class NP problems. So there are class P problems, class NP problems. And obviously P is subset of NP, class P problems, because you see, non-deterministic Turing machine will have much choices. So deterministic Turing machine, you can think of the way, it's a kind of part of non-deterministic Turing machine. So, but the question is whether P is equal to NP. This is still open problem, $1 million if you can solve. This is a fundamental problem of computer science. Whether class P problems, so whether P is equal to NP or P is strictly subset of NP is still an open problem. So for you, just a tea time problem, right? Can you try to prove whether P is equal to NP or not, right? And you get $1 million immediately. Or you show that P is strictly subset of NP, means P is not equal to NP. Either you show P is equal to NP or you show P is not equal to NP, right? So here your competitive programming is not going to work, right? By the way, these problems you can verify. So normally NP complete problems are those kind of problems which take exponential time to be solved, but they can be verified in polynomial time. Okay. Okay, so this was one. Okay, now before describing deterministic finite automata, I am again going to use slides of Professor Bush. Again, thank you. So I'm going to talk about languages. What do you mean by language? So when we're talking about machines, so machines should accept certain kind of languages. So what do you mean by language? Language is set of strings, very simple. So set of binary strings, binary language. Set of ternary strings, ternary language, right? Whatever alphabet you choose, right? So bunch of strings is nothing but a language. Actually, whenever you are speaking, say in English, Hindi, Gujarati, whatever language, right, you speak, so it is nothing but bunch of strings. Okay. So very, very nice connection that language is nothing but collection of strings. Okay. And what is a string? A sequence of symbols from some alphabet. And as you know, English had only 24 alphabets in 1600. I showed it to you, right? 1605 at the time of Shakespeare. Gujarati has how many? 56 alphabet size. कभी पढ़ा ही नहीं होगा, हाँ? हिंदी में कितने हैं, right? How much in Hindi? संस्कृत में कितने हैं? It's a very basic thing actually, you know. You should answer these questions first. Okay. Okay. If alphabet is A to A, B, C, D, Z, so language is cat, dog, house, right? These are the strings. So languages are used to describe computational problems. For example, primes, 2, 3, 5, 7, 11, 13, 17, and so on. Even alphabet is sigma is equal to 0 to 9. So normally, computation is translated to set of membership problem. Means, is this number x is prime? So x belongs to primes or not? That kind of questions you can ask. Okay. Okay. So now we are more formally saying that an alphabet is a set of symbols. Example, sigma is equal to a comma b. This is very, very fundamental thing from a computer science perspective, from even art side or even dance. You know that in the dance, basically, any dance, I don't know dance by the way, but you know, any dance can be composed of bunch of alphabetic dances. So basically there's a basic dance steps which can give you bigger ones. So it's all applying, you know, the same phenomena, you know, you can describe any dance. So there are things in the Indian literature about it. Anyway, so a string is a sequence of symbols from the alphabet. So basically if A is a string, AB is a string, right? AB, BA is a string. These are all strings. And normally we use variables U, V, W to describe the string. So these are known as string variables. Okay. U is just name basically. Okay. Okay. So decimal numbers alphabet is this 0 to 9, and these are the strings. Similarly, these are the binary strings at the bottom. You can see, right? Unary alphabet is very important for Turing machine. You will see later on how. Means unary numbers 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and so on, right? Or decimal numbers, right? So when there is a single alphabet having only one element, 1, you can represent all the numbers using 1, right? So that is there. Now, there are certain operations that are possible on the strings. Concatenation is very, very simple. So if you look at two strings, W and V of size N and M, for example, here you can concatenate, right? The first you put W and then V, just concatenate, concatenation operation. Very simple. This is all high school mathematics, right? If you have done from a good high school, right? So then, if W is this, A1, A2, AN, the reverse is reverse string, right? Reverse everything. Fine. Then we have length of the string. Number of symbols in the string is length. So here the length is n, here the length is 4, length is 2, length is 1, right? Now the time has come where we can confuse you a little bit. Soon I will show you something beautiful. So length of the concatenation is sum of the corresponding strings, right? Length. This is also straightforward. Empty string, this is a beautiful concept. A string with no letters is denoted by lambda or epsilon. Empty string. Okay? It has no symbol at all. But we call it lambda or epsilon. Empty string. So this acts as a neutral element. So observation, the size of lambda is 0 because it has no symbols. Empty string. And you can calculate it by W on either side. For a given string W, you will get W only. Right? Fine. Straightforward. Now you see the beauty. I will show you the beauty now. By the way, substring is something very simple. If a string is there, you take just some, some subset of the symbols, right? Consecutive, that will be a substring. And different kind of substrings are possible. Prefix and suffix. This is also very straightforward. Right. You can see that for that string, different prefixes and different suffixes are written. Right. Any question up to this point? It's very easy stuff, right? High school mathematics. Exponent operation. If take a string W and concatenate it n times, this is W raised to power n we can call. So AB BA square is AB BA AB BA, right? And so keeping this in mind, I can define W raised to power 0 as empty string. Analogy, right? Star operation. If sigma is alphabet, sigma star is set of all possible strings from alphabet sigma of all length. 0, 1, 2, 3, 4, and so on, right? All length. So sigma star. Okay. For example, if sigma is a comma b, sigma star is a string of length 0, then a string of length 1, there are 2, only a and b. A string of length 2, there are 4, and so on, right? Plus operation. Set of all possible strings from alphabet sigma except lambda. Lambda is not there, empty string is not there. That is sigma plus. So sigma star minus lambda. Okay, so this was all about strings. Now we can talk about languages. A language over the alphabet sigma is any subset of sigma star, because sigma star consisting of all possible strings, any subset, bunch of strings is nothing but a language. Okay, very natural definition. If sigma is a comma b, sigma star is this. So this is also a language, this is also a language, this is also a language. A bunch of strings. So any subset of sigma star is nothing but a language. Sigma is alphabet, sigma star is strings of all possible lengths. Any subset of this is nothing but a language. So this is also another example, A and B n where n is non-negative. So n is equal to 0, there will be empty string. N is equal to 1, you will AB. N is equal to 2, it will be AA, BB, and so on. Right? So this is a infinite language because you can keep on. So you just keep on vary n, you will get a string. Okay, even odd, we can leave all this useless. Two special languages. Now this is interesting. Empty language. There is no string inside. Language with empty string. Okay. Now you see, I mean, just see that. What is size of this? Empty language? 0. Size of this? 1 because it has empty string, right? And this is 3 and 5. So people do confuse here, okay? So empty language and language with empty string. Now note, phi is equal to singleton is not equal to singleton lambda, correct? And size of this is size of phi, which is 0, size of this is this, and size of lambda is 0. Lambda is empty string, it has no symbol. So size of lambda is 0. Okay? Crystal clear? Then you can define operations. This is very simple. You can talk about union of the strings, intersection, subtraction, and so on, complement. Sigma star looks like a universal set. You can do all those things, right? Basic operations. Reverse of a language. Reverse of a language is reverse of each string inside the language. Right? You can do that. If A, B, A, B, B, A, B, A is there, reverse of whole thing is everything is reversed. Right? Simple. Concatenation of two languages. We talked about concatenation of strings. Now we can describe concatenation of two languages, L1 and L2. Okay. It is XY such that X is in L1 and Y is in L2 because it's kind of concatenation, right? For each X and Y. You can compute that, right? For example, if this said, this is a language with 3 strings, this is a language with 2 strings, their concatenation is here. Right? One by one, you can do that. Another operation, L is to power n. Now, language power is n is L n times. And in special case, L is to power 0 is singleton lambda. This is different than a string raised to power 0 is lambda. This is singleton lambda. See the difference. And then what else? Clean star. This is star closure. All string that can be constructed from L is known as L star. So L is 0, L union L1, union L2, and so on. Positive closure, L plus. So the trivial thing is out. Done. Now we are ready with DFA. Again, these are the slides from Professor. So now we are going to describe deterministic finite automata. Very beautiful thing, very powerful concept. It is applied at different places in computer science, mathematics, speech processing, all kind of things. Viterbi decoding, right? Convolutional codes basically. So in communications, computer science, all beauty has to come from here. Okay. So DFA, deterministic finite automata. So we have, so overall structure is there is a input tape and there is some string on it. There is a finite automata. Remember what is finite automata? Bunch of states and transitions, right? And then we have output is either you accept that string or reject that string. Either you accept or reject. That is the computation you have to perform. Very simple thing. Okay. So for example, when you put some a coin in the vending machine, either you accept it and output is in that form, or you reject it, right? So either accept or reject. Now, normally, this is described with these kind of diagram known as transition graph, or So here we have initial state, Q naught. Normally, a state with this kind of symbol, this kind of arrow is known as initial state. These are intermediate states, and all these are transitions. And finally, when double circle is known as accepting state. Okay. Now, one thing I should emphasize here, depending upon the alphabet, suppose alphabet is having 2 symbols, A, B. In the DFA, in the deterministic finite automata, we should have a transition for each input A and B. So here you can see that even from here, if I get A, I know where to go. If I get B, I know where to go. Here also, if I get A, I know where to go. If I get B, where to go. For each state, I should have, for each input symbol, one transition. This is a very, very important requirement for DFA. So let me show you some examples. Okay, so this is what I mentioned. For every state, there is a transition for every symbol in the alphabet. This is a very, very important assumptions, right, for DFA. This is very important. You will see how we are going to use it for certain calculations. So now this is some automata is given to us, finite automata, input tape has A, B, B, A. And I want to know whether this automata is going to accept it or reject it. So starting from that arrow symbol Q0, if I can reach up to Q4, we are going to accept it. If not, we are going to reject it. So let us see what happens here. You read A, move to Q1, then you read B, move to Q2, you again read B, move to Q3, and again read A, move to Q4. So we accept it. Input is consumed and we are in the final state, so we accept it. Okay. Rejection case, A, B, A. You start with A, move to Q1, start with B, move to Q2, again read A, go to Q5. Input is finished and you are not in the final state, so you reject it. Okay. Any question at this point? Okay. What happens in this case? Tape is empty. Lambda. After receiving lambda, it will not move anywhere, right? So it will stay there itself. To rejection. Clear rejection at the start state itself. So this automata only accepts one string, which is A, B, B, A. Okay. So the question is, in your exams as well in your homework assignment, we are going to ask you this question. Given a language, find the DFA. Given a language, find a DFA which can accept it. Vice versa. So otherwise, on the other side, if DFA is given, you have to find the language. These two are the important things which you should know. Language is given, find the DFA machine. If DFA is given, find the language. This practice, accept, yes. So this is a very important exercise that you need to do. I think you can drink a couple of tea and coffee over the years, over the next few weeks before the exam, because this practice is required. I already posted the first assignment, so now you will see these kind of problems are there. So you can just do it on your own, you will learn, you will enjoy. This is really beautiful stuff actually. You will really learn how to design, how to do, programs, designing programs. So to accept a string, all the input string is scanned and the last stage is accepting state. Then we accept. To reject a string, all the input string is scanned and the last stage is non-accepting state. Okay. So this is the way we accept or reject. Yes. Pucho. इनपुट पे डिपेंड करता है ना इनपुट तो खत्म हो गया हमारे पास हाँ ये तो आई एम जस्ट गिविंग यू स्पेसिफिक एग्जांपल फॉर द स्ट्रिंग्स वेदर यू एक्सेप्ट दिस स्ट्रिंग और नॉट okay so essentially given a DFA you try so if I have to find a language for the DFA what I should do okay DFA is there you try different strings find a pattern normally there is a pattern right then you can see that the whole general pattern is accepted by the DFA okay so this is how you determine the complete language okay another example now DFA can have multiple accepting state as well this is also allowed so there in the previous one we have only one accepting state now there are three okay and if you are having three your job is very easy right you see that lambda is accepted anyway and the other one also is accepted right this is an example now let us try few strings on it AAB so you read A then read A again you are in the same loop then B you accept so AAB is accepted in this automata correct? Then BAB is a rejection case. You read B, you go to Q1, read A, you go here, read B, you again here, input is finished and you're not in accepting state, so you reject. Right? Got it? Okay. So that this automata accepts this. So see, we tried few things that we can guess a pattern. So the language accepted by this automata is A raised for N B. Why? Because you see, when we receive A, no matter how many times A is there, it will be taken care by this state, right? And as soon as you receive B, you go to this one, accepting state. So why do we need this then? Because from here, remember what was the condition for the DFA? For every input symbol, we should have a transition. So from this state, I should know if I receive A, where to go, and if I receive B, where to go. Right? So that's why I made this one. Now from there, again, I have to do something. So I have made a loop here. Okay. So this is an extra thing just to satisfy the definition. Otherwise, the job is done up to that point only. Right? Got it? Any question at this point? Another example is sigma is equal to 1, so unary. So even all even strings 1 1 1 1 1 1 kind of thing will be accepted by this, because if one you read it and you come back, right? No matter what is the, if it is equal number of ones, right, even number of ones, it will be accepted by this automata, right? Very straightforward. So formally, a DFA is 5 tuple Q set of states, sigma input alphabet, delta transition function. I'll tell you explicitly, I will write this transition function. Q naught initial state and F set of accepting states. There are couple of, need not be one only, right? There could be many accepting states, right? You just saw in the example. So here is an example. In this example, Q is Q naught, Q1, Q2, Q3, Q4, Q5, all the states, right? There are 6 states altogether. Sigma is A comma B, right? What else? Sigma is A comma B. Initial state is Q naught. Set of accepting state, there is only one. F is equal to Q4, which is subset of Q, right? Transition function we should describe. Transition function, delta is reading some symbol. So you are in state Q. After reading some symbol, where do you go? That's what we are doing all the time, right? So transition function can be described like this. So here delta of Q naught A. Delta of Q naught A is Q1. Delta of Q naught B is Q5, and so on. You can write down all the transition functions, right? So now once you are able to do that, actually you can simplify your work. You can write down all the transitions. You actually basically you can make a table for each state and for each input symbol what should happen. So this is nothing but a program for your whole automata. Now you don't require picture. Now you don't require picture, right? You can do everything from this program only, right? This table. For programmers, this is very useful thing, right? Just make the table and tell what to do, right? So this is the complete program for. By the way, similarly, I will show you, or I will tell you that you should write a computer program in terms of Turing machine, how to add 2 numbers, multiply 2 numbers, and so on. So again, programming will be in this kind of table actually, in terms of these transition functions, okay? Then we also describe what is known as extended transition function, delta star. So delta transition function works on single symbol. Delta star works on a bunch of symbols. Okay. So basically, so you are in state Q. After reading a string W, you go to another state Q prime. Okay. After scanning the string W. So here is delta star Q naught AB. So you are here. Delta star Q naught. You read A and then you read B. You get into Q2. Right? So delta star Q naught AB is Q2. Similarly, you can have another one. So one special case, delta star Q comma lambda. When empty string is there, you will be in Q only, right? This is a special case. In general, delta star Q comma W is equal to Q prime. So you are in state Q. After scanning the string W, you go into Q prime, right? So this can be broken into many intermediate steps, right? Because you can go into one symbol at a time, right? That is a possibility. So now we can describe formally language accepted by DFA M. So it is denoted by L of M. Language is accepted by M. So contains all the strings accepted by M. Then we say that M recognize L. So here for a DFA, we can describe mathematically, for if DFA is like this, language is all those strings in the universe which starts from Q naught with a delta star transition. After scanning W, you belong to one of the final state, right? Mathematically, you can describe like this. Fine? Any question? Very straightforward. Rejection case, when it does not belong to final state, right? All those, okay? Now more DFA example. You look at this. This is a beautiful example. For empty language, this is the automata. See, for empty language, this will accept empty language. Do you agree? कोई string है ही नहीं ना. And what about this? This will accept all strings. This symbol is there because to cover the definition for every state and every symbol, there should be a transition, right? If sigma is A comma B, we should know where to go. If I receive A, we should know where to go if I receive B. Similarly, there also, right? But that accepts everything because everything is accepted there, right? And here, because there is no accepting state, it's an empty one, right? It will not accept anything. Now, language of the empty string. So, do I need this? If I only start like this, start state in double circle, this should accept this lambda, right? Why do we need this? For every symbol, that condition, right? For every input symbol, I should have a transition. So that is that's why we require this, okay? Now I think I talked about one way. From the DFA, I showed you the language. Now I will give you one example of a language and how to construct the DFA. Okay, the reverse. So sigma is A comma B. Language is given to you all strings with prefix AB. Now listen it carefully. How do we construct the machine DFA? All strings with prefix AB. Starting में AB आना है, right? And then all strings. So what I should do? I will start from Q naught. This state, start state. Then you know what to do. A, after receiving A, I have constructed this state. Then after receiving B, because B should be there, we know the first two symbols are A, B. B, we go here, and then I should accept it, right? This much we have done. But now I need to take care of the other conditions that are there. For every input symbol, there should be, transition, right? From each state. So I see, okay, what is left here? So I saw that from here, if I look at this state, I should know if I get A or B, what should I do? So I just do a self loop. So this is taken care of. Now you come here. Here after A, where I should go, it is given, but B I don't know. So I created another state Q3 and I assigned B here. I arrived at here. Okay, but then again here also I should take care of A and B. So another self loop here. Okay. So this is all done up to here, and so we are ready, right? Now the question is, somebody will ask, here I have used 1, 2, 3, 4 states. So for a given language, somebody will use 5 states, somebody will use 10 states, right? Which one is correct? This is your common problem, right? मैंने तो सही लिखा था, right? So it's okay. I mean, see, how your brain thinks, you may come up with a solution with 5 states, somebody can come up with a solution with 6 states, and so on, right? Obviously, the best one is which uses least number of states. Okay, so basically the question is, given a string, how do you find the least number of state automata that can accept it? Now, when I say that, actually, when I'll talk about NFA, non-deterministic finite automata, I will show you construction of NFA is very easy as compared to DFA because those conditions are not there. And from NFA, every NFA can be converted into DFA by certain transformations. So I'll talk about this in the next class, I guess, when how do we convert it, okay? I think one or two examples are there, or I'll leave it. Yeah, so this is for all binary string containing substring 001, without substring 001, for all. So in all those strings where the first letter is A and last letter is A. So what is the definition of regular language? A language L is said to be regular if there is a DFA that accepts it. So all those languages which are accepted by deterministic finite automata are known as regular languages. Okay. These are examples of regular languages. You can see the question is there any language which DFA cannot accept? All these are accepted. There exists DFA that accept these languages. Of course, you can construct. So this is a T time problem. You can just work out. I think some of them we have already done, right? So the question is, can you give an example of a language for which DFA cannot be constructed? That is a beauty. So that will show that there is a limitation to the DFA. This machine has limitation. What kind of language is that? The answer is A and BN. A and BN, where N is non-negative. This cannot be accepted by any DFA. Why? How? Think over T. We can come back to this question next time. A and BN. A and BN. Okay, like that. This is the A and BN. There exist languages which are not regular. So this is an example of a language for which you cannot construct DFA. तो सोचने की बात है क्यों? तो चाय पे चर्चा. Think about it. Right? So this is all about. काफी हो गया ना? Next time I am going to cover. I am sure I will be able to cover. आज मैंने बहुत कुछ cover कर दिया. Next time I will cover NFA, conversion of NFA to DFA, and PDA. 3 तो हो जाएंगे. Right? Thank you.